This video is on development length, cracking, deflection and torsion. All these things are needed when you are doing a complete design of beam. So far in the course we have only done moment capacity, we have only done shear, but now it's time to learn a complete design of beam and this is the background. Now first is concept of development length. Now let's see a situation where there is a bar embedded in concrete and I want to pull it out. Now will it slip? It depends, or will it be pulled out easily? It depends on how much length is embedded. So here is a concept of LD, that is development length, which can be easily understood if you look at this equation. On the left hand side, it is tau BD pi d LD. What is pi d LD? The surface area of the bar, and tau BD is the bond stress. So if this more than this force is applied, then the embedded bar will come out. So if I equate these two, sigma s pi d square by 4, where pi d square by the cross section area of the bar and sigma s is the allowable stress, then we can get expression for LD. So if you want to know how much development length to provide or how much development length is needed, then this formula comes handy. And for tau BD, there is bond stress. code gives this table. Let's understand what this table says. It gives for M20, M25 and M30, and values of tau BD are 1.2, 1.4 and 1.5 Newton per mm square. Now see the note 1. Tau BD, whatever given here, shall be increased by 25% for bars in compression, if they are in compression. And if the bars are in tension, then for high strength bars, the value of tau BD shall be increased by 60%, increased by 60%. Now, what you should do is using this and using this formula, try to work out these numbers in or verify numbers in this table. For example, now what this table is, Fy gives the strength of the steel. We will be only dealing with 250 and 415. There are bars in tension and there are bars in compressions. Okay. Now look at the bar in tension and look at in front of 415. It is 47 times D. 47 times D. So how this 47 number has come, you should check yourself using that formula. What it means is that if I have a bar of diameter 12 mm, then 47 into 12 is the development length needed for 415 concrete. Now there is something like anchorage value, that every bend you get 4 times the diameter, every 45-degree bend you get 4 times the diameter bar as anchorage strength. Now let's take this situation. This is a cantilever beam and it needs 225 bars at top. Now you see the length available is 1000. Is it sufficient? Let's check out. 25 is the diameter of the bar, 47 times 25. This 47 number I got from previous charge. What you need is 1175 and what you have is 1000. So development length is not enough to develop full stress in the steel. So perhaps if you are doing it, you may want to bend this bar a little bit downward and you will be okay. Next, look at this. Look at the bottom reinforcement of this footing, and from the face, if there is 12 mm bars, then 12 into 47 is what is needed, and what is provided is 700, which is more than 700. You can subtract 50 mm cover, so 650 is more than 12 into 47. 12 into 47 comes to 564. So this width of the footing beyond column is sufficient to develop the stresses. So this is how development length is. One more, let's do this example. Suppose I embed a 12 mm bar in concrete for 100 mm. I want to know with what force I can pull it out. I'm using formula LD sigma SD 4 into tau BD. Okay, I reshuffle the formula to get sigma S. Now LD is 100, tau BD is from the previous chart, which is I think here, 1 minute, yeah, 1.2. Then D is diameter of the bar is 12, so you get 40 Newton per mm square. And then P will be this stress into area of 12 mm bar, that is 130. So if you apply 4.52 kilonewton, then this bar will come out. So whatever load you want to attach, let's say this is a fan, a rod, so how much you should embed? So it restricts the weight of the fan to less than 4.52 kilonewton. Now this was about development leg. Now let's talk about deflections. As you know from structural analysis and so on, deflection calculation is lengthy, and therefore code has made your life easier. They are saying the deflection shall not exceed span by 250. And if you're doing architectural purpose, structural purpose, span by 250. Architectural fixtures and all, if you want to keep them safe, deflection shall not exceed span by 350 or 20 mm, whichever is less. But again, to calculate deflection, there will be a lot of work. So instead of that, what code has suggested this for spans up to 10 meter. Okay. Span to depth ratio. If you can maintain for cantilever 7, simply supported 20 and continuous 26, deflection criteria is automatically satisfied. You don't have to do any calculations. And for spans more than 10 meter, this you multiply by 10 upon span. So this way, when you design, you just apply this deflection check. When you do a full problem, we'll again demonstrate it. But this is a very easy way of doing it than calculating deflection of your designed beam. Then cracking also, see what they say is depending on the exposure, the crack width can be 0.3, 0.2, 0.1. For moderate exposure, it is 0.2 mm. But again, see, crack width formula is also quite complicated. So what code has done, by and large, it has suggested smaller diameter bars well distributed in tension zone, and it has suggested the maximum spacing. Look at beams. If you are using 415, then spacing between two main bars should not exceed 180. If you do that, cracking criteria is satisfied. Similarly for slabs, spacing of the bars, main bars, should be lesser of 300 or 3 times effective depth, and for distribution bars it should be lesser of 450 or 5 times effective depth of the slab. See, this is an easy way for design. You adopt these norms and you don't have to check for cracking. It's automatically satisfied. Torsion, you know is again very complicated. They have made your life simpler. They say that if you have torsion TU and moment MU applied to the beam, then modify MU by this formula to ME, where MU is the factored moment, T is the factored torsion, D is the depth of the beam, and B is the width of the beam. And similarly for shear also, if there is a torsion, instead of VU, you use V equivalent. So see, complicated thing, they have made it simpler for the design. So this was all about, I would say, development leg, deflection and cracking. and its use will be demonstrated when we will do a complete problem on beam design. Thank you.